All right, so these are the types of questions that you get on the end of course exam, where there's usually some type of context. Like question 8, that's probably not going to be, or 7, it's probably not going to be on the end of course exam, something like that. That's very simple, straightforward. They're more like these, make you think a little bit. It says a 2.5 foot wide circular track for a camera or dolly is set up for a movie scene. So the two rails of the track form concentric circles. The radius of the inner circle is 70 feet. How much farther does the wheel on the outer rail travel than the wheel on the inner rail? So what we need to do here is, if we're talking about the distance a wheel travels, we're talking about circumference, right? Okay. So if I'm talking about circumference here, what is the formula for circumference? 2 pi r. Okay. Circumference equals 2 pi r. Okay. Now, what they're showing me here then is that for this wheel right here, or this inner track, it has a radius of 70 feet, correct? So if I want that circumference, it's 2 pi times 70, which is 140 pi. Would you agree with that? Okay. Now, this is showing me the distance between the two rails. That's not showing me the radius of the outer rail, right? This is basically showing me the axle length of the dolly. Does that make sense? Okay. The radius of that outer circle would be this 70 plus that 2.5, wouldn't it? Does that make sense to everybody? So when we go circumference equals 2 pi r, we're now looking at 2 times pi, but r being 72.5. And now if I go ahead and multiply, so 72.5 times 2, okay, what's that going to be, 145? Times pi. So now, the difference between those two is 5 pi, right? Okay. So if I multiply that by, just multiply that on my calculator, I get to the nearest tenth as they want. But that outside wheel is going to travel further. Okay. We'll talk in trigonometry about, because of this relationship, because that wheel is going to travel a longer distance in the same amount of time that this wheel has to travel this shorter distance. This wheel here is actually moving faster than this wheel here. Does that make sense? Okay. It's called linear velocity that we'll talk about in trig. No, you got to multiply that. You got to take your calculator. So whatever 5 times 3.14 ends up being, 15.7 or something like that for my problem. Anybody in track? When you're in track and you run like a 200 meter, okay, you all stop at the same spot, don't you? Finish line is always the same spot, but you're going to start like this, right? They're going to stagger you. Why? Yeah, because these people out here have a longer radius to turn than what these people in here do. Does that make sense? So in order to get you all to stop at the same spot, they need to stagger you so that you all run the equivalent distance, okay, or the same distance. If you're anybody just like go out to the track and just like to run like long distance, I like to run long distance, but I don't like to do it on the track because it's really boring, right? But I want to get miles in quicker if I'm ever on the track, okay? So generally, we say 4 laps around the track gets you a mile, right? Okay, or close to a mile. If you were ever to do that, like go run 1 mile on this inner track, lane 1, and then go to lane 7, okay? If you stay in lane 7 the whole way around, it only takes you about 3 laps to get your mile compared to the 4 laps that you need when you run on the inner lane. Does that make sense? And it's all because of that radius being longer. It's kind of like you're the outer wheel on this problem here versus being the inner wheel. Okay, you have a longer distance to travel. Any others on there? 9. What's the formula? Finding the arc length. Okay, I need to know. So if I went all the way around, so circumference would be 2 pi r, right? So circumference would be 2 pi times 10 or 20 pi. That's how far, if I went from here all the way around and got back, right? I'd travel 20 pi centimeters. But I'm not going the entire circle, right? So I need to multiply by the portion, okay, or divide this by how many of these little sections here can be put in there. Does that make sense? And the best way to do that is not actually to divide, but to multiply by this ratio to the whole circle. So 45 compares to 360 by a 1:8 ratio, right? So if I just travel that little red segment or section, that arc, I'm only traveling 1/8 of that 20 pi. So I take 1/8 times 20 pi. Okay, and it says type your answers exact. So this 8 and this 20, they carry a factor of 4, right? So I'd have 5 pi over 2 as my exact answer. Okay, now the quick way, you can do it that way, find the circumference and then find the portion of the circle that you're really interested in. But this formula, arc length is equal to x over 360. That gives you the 1/8 times in 2 pi r. So this gives you the portion of the circle times the circle circumference, and that will give you what you need there. Does that make sense? And that is important for what we talk about today, because we're gonna alter it just a little bit. Any others on here? Let's go on to talking about today's stuff. I did send you a email about 20 minutes ago, giving you the layout of the next 3 weeks. Okay, so the next 3 days or 3 weeks in 1 day, because then the Tuesday of that 4th week you take the end of course exam. There's some things that I'm interested in demonstrating, getting you exposed to a little bit before you take that exam, which we're not as far behind as I had anticipated when we started September 8th. We've had a lot of cancellations. We've had all these 2-hour delays. We've kind of made up time as we've gone through the year. So right now, what I'm really concerned about over this week is we're going to talk about circle areas today. And then the rest of the week, we're going to talk about circles, 2-dimensional circles, okay? Things called tangent lines, inscribed angles, equations of circles in the Cartesian plane, that kind of stuff. We're going to do that this week, okay? That's not going to give you everything you need to know about circles, but it's going to give you the things that predominantly show up on the end of course exam. It's going to give you some work with those, okay? When we get to May and we finish the end of course exam, we'll come back and hit some of those sections about circles that we skipped this week, okay? Next week, we'll do transformations, which you have some exposure to those things, okay? And there's only 2 2 downloads off of Schoology dealing with those notes. It's 4 sections, but they pair up pretty well. So that's the way I've got them set up in Schoology. And then starting the 19th of April, we'll start a week worth of probability. Okay, and I think those 3 weeks will give you a good preview of the information that is usually asked in the course exam. My intentions are, at this moment, not to have in-class tests or quizzes in the next 3 weeks, for the mere fact that I don't want to chew up valuable class time with you guys. But in their place, I'll open like a take-home test or a take-home quiz. If it's a take-home test, I'll give you a week to do it. If it's a take-home quiz, I'll probably give you the weekend to do it. Okay, because it'll be quite a bit shorter. So those things are open. I sent you the email just for those of you that like to print stuff off, so that you have the ability to do that before class starts tomorrow. But we will start with 12:1 tomorrow. Do you may have questions on that, Connor? The whole you want one? Yeah. You could do the optional reviews. I can maybe see. I think, at least in the past, the state has provided some practice tests. I can maybe get you. We will have to sign up and that kind of stuff. I think create accounts, but I think we can do that. I can open the reviews back up too. Yes. Yeah. Don't let the end of course exam scare you, worry you. You guys will all do fine on it, okay? But I want to make sure that you've seen the things. I don't want something to show up like the equations of a circle, and you have absolutely no idea how to do that problem, okay? Then they could have, because we're going to skip over some sections. But just going off of my knowledge of what's on that test or what's been on that test in the past, I think I've selected the main sections that are going to be that we haven't covered yet, that could potentially show up. I think we'll be okay. Today I want to talk about areas of circle, or areas of circles. This is not extremely difficult, okay? And one thing I guess we should talk about is there's an entire chapter of surface area and volume that we're not going to get to, but you guys talked about surface area and volume in 7th and 8th grade, correct? Okay. If you need, generally they give you a reference sheet that has those formulas on them if you need them. In the past, surface area and volume is not a huge topic that they talk about on the geometry test. But the reason I'm skipping that, and we'll talk about that chapter mostly at the beginning of May, last week of April, beginning of May. But you have exposure to it. You've previously seen it and understand the concepts where you can work your way through those problems if they are presented to you. So everything in this chapter will build into volume and surface area. So what happens with, if I want to find the area, or sorry, not the area, the volume of say a cylinder. Now let's think about it this way. Let's go. If I want to find the volume of this book, okay, how much three-dimensional space this book takes up? The idea, and this is a calculus concept, is that if I find one area of this piece of paper, okay, and I say it's got a thickness, but let's say that thickness is infinitesimally small, okay? If I can find that area and then stack a bunch of those on top of each other, which is what a book is, right? A bunch of rectangular areas stacked on top of one another. Even if I add that area to that area to that area, to that area, all the way through the book. Okay? Add them all together. What do I get? I get the volume of the book. Does that make sense? Okay? And the way that I would find that volume quicker is I would take this area, length times width, and then multiply it by this height right here, and that would give me the volume of the book, right? Does that make sense, everybody? And that multiplying by the height is the repetitive addition of one page area plus the second page's area plus the third page's area. So all shapes, when we're looking for volumes, all of our shapes are using that approach. So what I'm getting at is the area of the circle, when we get to volumes, we'd be interested in maybe finding the volume of a cylinder, volume of a pop can, volume of a water bottle, something like that, okay? So we'll come back, and we might struggle with it in chapter, I think it's chapter 11, at the beginning of May, if we struggle with it at May, I'm fine with that. We'll have to go back and maybe, I say the struggle, but it's because we'll struggle remembering some of the area formulas, okay, that are then used to find our volume formulas. That's why these two chapters, 10 and 11, piggyback off of each other, because 11 uses everything from 10. But because of the course that we're going to take, we're going to bounce around. There's going to be about a 3-week gap before we get to chapter 11. So we might have to come back to some of this stuff. Okay, but right now, area of circle, you guys know from previous years, pi r squared, right? Okay. Always remember, I always get people to confuse these. 2 pi r squared. Okay. Which one is dealing with area? Well, we talk about area, square units, right? Area is always square units. The only way that I can get square units is looking at the pi r squared. Because if I look at 2 pi r, 2 doesn't have units on it. Pi doesn't have units on it. R will be like centimeters or meters or feet or inches or whatever. But there's no other centimeters, feet, miles, inches to multiply. So this is going to be a first degree result, which means it's got to be linear. Okay? That means that's a length, circumference. Here, okay, pi doesn't have units, but R will have centimeters. So you have centimeters times centimeters, or it might have inches. So you have inches times inches. And that'll give you inches squared. And when we talk about things that are squared, inches squared, feet squared, whatever, that's an area, right? So that's a way that you can remember which one's which, okay, by knowing what our units look like for an area and what our units look like for a one-dimensional length. Okay? Is that all right? So pi r squared. Now, what we're going to be really interested in today is actually finding the area of a sector. Okay? A sector is the region bounded by 2 consecutive radii in what we call a subtended arc. Okay? S to R is referred to as a subtended arc, meaning that it's just the arc that encloses our central angle. Okay? But that yellow shaded region looks like a piece of pizza, piece of pie, whatever, right? It's almost triangular. It's actually going to be bigger area than a triangle, but that is called a sector of a circle. Is everybody okay with that? We'll be interested in finding that thing's area. Okay, it says to find the area of a sector, you find the portion of the sector in relation to the whole circle. Okay? So what happens is that we're going to be interested in finding this area right here. Okay? If I know that the measure of AB as a degree, let's say it's equal to 60 degrees, would I know that A to B, let's actually make it so it looks a little bit more to scale. Let's say it's 120 degrees. Would I know that arc AB is 1/3 of the entire circle? Because 120 compared to 360 reduces to 1/3. Does that make sense? Okay. So this arc AB would be 1/3 the entire circle, its circumference, but that shaded region would then be 1/3 the entire circle's area. Okay. So this formula down here area of a sector, if you remember from the length of an arc would have been arc AB's measurement divided by 360 times 2 pi r. That's what we talked about on Thursday in the beginning of the class today. This formula is the same concept, but instead of multiplying by circumference, we're now multiplying by area. Okay? So this is asking what portion of, because multiplication means of, right? So what portion of, or what percentage, okay, we think about it that way, of the entire circumference. This is what portion, what ratio, what percentage of the entire area. Is that okay with everybody? It's the exact same setup, exact same structure, and exact same reasoning of the length of an arc formula. So this type of question they're going to give you. Okay, this is what is the area of sector GPH? Leave your answer in terms of pi. Okay, I always fight with students, not like physically, but we argue about, what is easier. Okay, if I leave my answer with the symbol pi in it, that should be easier or less time consuming than rounding to the first decimal place, second decimal place, that kind of thing. Okay, and what I mean by that is if I want to find the area, okay, we're going to go x degrees over 360 degrees times pi r squared. Okay, x in this case is 72 over 360. Okay, and they could give that 72 in two different locations. They could give it as the arc measurement, or they could give it as this central angle measurement, and we know that they are one-to-one. They are the same thing. Okay? And they'll multiply by pi, and then r squared. So 72 over 360 is what? One-fifth? Okay. Times then pi, anybody know what 15 squared is? 225. Okay. Now 1/5 times 225. Those two numbers, those are rational numbers, right? Let's multiply those together. Those two work together the best. So basically I'm asking you 225 divided by 5. How many times does 5 go into 100? 20, right? Okay. So it's going to go into 225 45 times. That makes sense? Okay. And then I get pi. So 45 pi. Now, I could change that to 141.3717. But what would I have had to use to get that answer? Would have had to get a calculator out, right? Did I need a calculator to do that? No. So I didn't have to rummage through my book bag, find my calculator, turn it on, find the pi button, multiply by 45, all that kind of stuff. This was easier. It's more abstract. If I asked you, I need you to go to, maybe we're making like a circular like patio, and I tell you to go to Lowe's and get 45 pi square feet of pavers, you're going to look at me like I'm an idiot, right? Okay. And you would grab your calculator and say, okay, I need 141 square feet or more than that, okay? But there's applications for this. There's purposes for leaving it as 45 pi. Algebraically, it's easier, okay? The answer is more abstract, but the procedure is easier. It's less work. Is that something we can do? Let's look at what would the area. Let's do it this way. What would the area? We'll use our calculator to make this connection. So if I go pi times r squared, so r was 15, so 225, right? Okay, and we just got 45 pi as our answer. Okay, if I take, so I'll call this B, and we'll call this T for top or numerator, bottom for denominator. If I take top divided by bottom, what number is that? Well, let's do this. Let's go 0.2 times 360 degrees. What's that give me? 72, which was a 72 here, right? Okay. So we're showing that we compare this yellow area to the entire area. This is 0.2 of that entire area. Okay. Do not go off of images. Okay. They try to draw this somewhat relative to the size of the circle, but I would not say, well, I can just visually put 5 of these in there, because that's what 1/5 is 0.2, right? So this is showing 1 out of 5 of these sectors, or 5 slices of the pie. I would not go off of looks. Okay, that's gonna be problematic for you if you do that. Okay. Here it says a circle has a radius of 4 inches. What is the area of the sector bounded by a 45-degree minor arc? So here they don't give you the picture. You need to draw it. So you got my circle. Radius is 4 inches. Okay, this would be the sector that they're talking about. And the minor arc that they're saying is bounded by the minor arc. That's 45 degrees. So area equals x over 360 times pi r squared. X in this case would be what? 45 times pi r would be 4. So if I square that, I get 16, correct? What's 45 out of 360? 1/8 times pi times 16. That number there and that number there work best together. What's 1/8 of 16? 2. So 2 pi inches squared would be the area of that shaded region. Is this something that we can do? All right, now, they screw with us a little bit, because the next thing they want to know is the area of a segment. And I don't know why, when I converted this over from a PowerPoint to a PDF, I just put the picture right in the middle of the words. But a segment of a circle, it's kind of like the crust of the pie, or the crust of the pizza, a piece of pizza, or piece of pie. Segment of a circle is a part of a circle bounded by an arc, okay, and the segment joining the endpoints of the arc. Okay? So if you remember from Thursday, we called this segment a chord. Okay? So the segment of a circle is the area bounded by that chord and its accompanying arc. Okay? Now, we don't have a formula for that segment. We don't have a specific formula for that thing. Okay, to where I could take maybe the chord length and multiply it by the arc or something like that. We don't have something that is very direct for finding that area. Okay, so we need to develop a plan. Okay, and the plan is right here. It says to find the area of the segment, you find the area of the sector, and then subtract away from it an area of the triangle. So I'm going to show you these things right here. Okay, so our end target, our end goal is to find that area right there. Well, that area right there, if I connect the endpoints of the chord back to the center of the circle, so back to there and to there, okay? You can see then that you would have that sector, right? If I can find the area of that sector, okay? And then when I come back and connect the chords again, can you see this triangle right there? We should have all the values that we need to find the area of that triangle, which is in that middle picture. If I take the sector area and subtract away from it the triangle area, is that going to leave me just the sector area? Or sorry, the segment area. Does that make sense? So sector minus accompanying triangle is going to equal segment area. And that's the way that we're going to have to do every one of these problems. Now, the nice thing about the area of that triangle is always going to be what kind of triangle? If that's a radius and that's a radius, it's isosceles. It might be equilateral if this was a 60-degree angle, okay? But it will always at least be isosceles. And if it's isosceles, then we'll be able to use that distance right there as an altitude. And that'll be h. And then this will be our b, okay? So every one of these problems, that's the hardest part of these problems, is find the area of that triangle. But my hopes are that we've done enough triangle work that we can be able to do that. All right. So here's a question they want us to work on. Find the area of that yellow segment. And we call it a segment of a circle. We find its area knowing that the radius is 18 and that central angle is 60. So the first thing I always do, I know I need three things. I need the area of the sector, and I need the area of the triangle, and then the final thing will be area of the segment. These two things can be found independently, meaning the order doesn't really matter. But once I have those two, I subtract in to get this one. So area of the sector, that's exactly what we're working on right now. Okay, and this entire section was finding everything that is now yellow, right? Okay, so to find everything that is yellow, I'm going to take x divided by 360, where x is the arc that bounds the sector, and then times pi r squared. Well, x divided by 360 would be 60 divided by 360 times pi times r squared. So we get 1/6 times pi. Anybody know what 18 squared is? Nope. 324. Okay. And then 324 divided by 6. How many times does 6 go into 32? 5 times, right? And you would take away 30, so it'd give you 24 left over, right? How many times does 6 go into 24? 4. So 324 divided by 6 ends up being 54, and times the pi. Is everybody okay with that? That's the area of the sector. Now we've got to find the area of the triangle. Okay. Well, triangle formula is 1/2 BH. Okay? That distance right there is the same as that distance right there, correct? It's radius. So it's an isosceles triangle. I'm going to draw this down. That distance is going to be h. It's our altitude. Okay? But think about what we just created. I'm going to draw my triangle just so it's a little bit bigger and easier to see. If that's C, that's my central angle. Let's say that's B and that's A. What I just drew down was H right there, correct? Okay. Now, the reason I need to know that this is an isosceles triangle, do you remember what drawing that segment in an isosceles triangle, if that segment right there is perpendicular to the base, does anybody remember what it does to the base? What does it look like it does to the base, the way I've drawn it? Bisects it. So those two distances are going to be the same, which is going to be nice for us. Does anybody remember what it does to the angle up here? Bisects it. So it started off that angle being 60, right? Now it's 30, correct? This is 60. Do we now have a special right triangle right here? Do you know one of its side lengths? You know that's 18, right? What side is that in a 30, 60, 90? 2n. So n would be 9, right? So you see if that's 9, what would h be? 9 radical 3. So when I fill in the area formula for my triangle, it's 1/2 b. We'll talk about b here in a moment. We know h is going to be 9 radical 3. What do you want b to end up being here? Do you want to find the area of that triangle? If we're to find the area of that triangle, b would be what number? That red triangle is that one right there. B would be 9, right? But our goal is to find the area of that entire red triangle, right? Which would be this entire triangle down here. So what should I let B be in that case? 18, right? And that's why we talked about this distance right here, this altitude, bisecting the base. Okay? Because because basically what's going to happen every time is that you're going to find that distance there. And then you need to double that to end up getting the area of the overall triangle that you're interested in. So this would be 18. So those are canceled, give me 9. So 9 times 9 is 81. So I got 81 radical 3. Okay? Which one of these is bigger? Would you guys agree that or just tell me, is the area of the sector, which would be that area right there, is that bigger or is the area of the triangle bigger? Sector is bigger. So the way I need to subtract these would be area of sector, which was 54 pi, minus area of triangle, which was 81 radical 3, and everything was in inches, so this would be inches squared. And that's your final answer in terms of exact values. Okay? And what they generally do with something like this is they will try to make, and it doesn't happen, I'm not saying it's going to every time, but they like to make that angle 60 degrees, they like to make it 90 degrees, and they might like to make it 120 degrees. Because when I cut those in half, I get 30, 60, 90, or 45, 45, 90 triangles that I can use special right triangles to find the dimensions of the triangle. Okay? If they don't do that, let's say they say that that angle's 68 degrees. Okay? Then you cut it in half, you get 34, and now you have to use SOHCAHTOA to find lengths. Okay? Does that make sense? It's the same thing that happens. So we don't have a formula for this. Remember going back to, we first did areas of these shapes. Before we had a formula, we had to say, okay, well, we got that area there of that triangle plus the area of that triangle plus the area of that triangle plus the area of that triangle, right? Or if we come up here, before we had the area of a trapezoid, we had an area of a rectangle plus the area of a triangle, okay? Those were additive procedures to find areas. This is a subtractive procedure to find an area. Why don't you guys take a minute and see what you can come up with for, do number 3 here first. So we'll find the area of that yellow region. Did you guys get 4/3 pi for the area of the sector? Okay. Now the area of the triangle, we're going to draw that down every time. That's going to be h. Okay. Now if this arc out here is 120, what is this central angle right there? Also 120. H, though, does what to that 120? Good. So we get 60, and now here's going to be 30, right? So this distance here is your hypotenuse. That's your 2n, right? And they're saying it's 2 in this case. So what would n be? N would be 1. And that's going to be the h value, correct? That's the distance across from 30 degrees. That distance right there is going to be 1 radical 3. Okay? So in trying to find the area of my triangle, I can go 1/2 base. What do you want your base to be? 2 radical 3? If I go 2 radical 3, that's going to be that base right there, correct? Okay? And that's the triangle I want to find the area for. If you don't do that, if you let B be radical 3, that's fine, but it only finds the area of that triangle. If you do that, what would you have to do to find the area of the entire triangle? You'd have to double it. Okay? So just be cautious of that. And then H, we said, was 1, right? Did you guys get radical 3 for the area of your triangle? Okay? Then sector, which would be 4/3 pi minus radical 3, which would be your triangle, should be the area then. That is yellow here. And that's going to be meters squared. You know, as I said earlier, you might not always be able to get a nice 120, 60, 45, 90, whatever. Okay? So here it's the same idea. Now, they don't ask me to find the segment here in this picture, but that's what we're going to do. So let's draw this down. I want to ask to find that blue segment. So I'll find the area of the sector first. It's going to be x over 360 times pi times r squared. So I get that. Now 75 and 360 aren't real nice numbers together. We should be able to So I go 75 by 360. This gives me 5/24 times pi times 81. And this gives me 135 over 8 times pi. Okay, and that's just working through, figuring out common factors between these, the 5/24 and the 81. Is everybody okay with that? Okay. Now I got to find the area of the triangle. Okay. It's not going to be as easy. And I'm going to draw my triangle. So that's 75 there. That's my central angle. I'm going to draw this straight down. We know that this is 9. Okay. Now when I break that 75, it's not going to go down to 60 or 30 or something real nice, right? That 75 divided by 2, what's 75 divided by 2? Okay, not a real nice number, right? Okay, so in that case, we have to use what to find H and B? You got to use SOHCAHTOA. Now, H would be what side to this 37.5? Okay, H is the adjacent to that 37.5, so that's the adjacent, and 9 would be hypotenuse. So what am I going to use to find H? Cosine. So I go cosine of 37.5 is equal to H over 9, right? And then 9 cosine of 37.5 is equal to H. Okay, that's great. Let's call this B right here. Okay, and that would just be that red distance. What trig ratio would I use to find B? Because it's the opposite side, right? So sine of 37.5 is equal to B over 9. So we go 9 sine of 37.5 is equal to B. Is that okay? What do I have to do with that B, though, to be able to get the area of the green triangle? Need to double it, right? So if I double this, that would make this entire thing B. So what's 2 times 9? So 18 sine 37.5 is the base of my triangle. So now, area is 1/2 BH. 1/2 B was the 18 sine of 37.5. H, we said, was 9 cosine 37.5. This 1/2 and this 18 work together nicely, gives me 9, and that 9 and that 9 go together, give me 81 sine of 37.5 cosine 37.5, and that's the area of my triangle. So if I want the area of the segment, okay, now here's the thing, and I haven't used my calculator yet, and I don't want to, but in most of these questions, when they tell you the central angle is like 75 or some obscure angle, they're going to ask you to type your answer in using tens place, hundreds place, thousands place. So at any juncture here, if you feel it necessary for you, once you found H, if you want to type that in and get that into a decimal, you can. Okay? If you get down to right here when we had that B and you want to change that to a decimal, go ahead and do it. And then you would double that, right? And then you could use all that. But what that does, when I round those and I start plugging those into this formula here, I compound the error that I generated when I rounded them up here. And I just want to be cognizant of that and try to avoid it. When I write this answer as 135 pi over 8 minus 81 sine of 37.5 cosine 37.5, there is not going to be a single problem that asks you to write your answer that way, but that is the exact answer because none of those values have been rounded. Does that make sense? When we get to trig, we'll demonstrate in trigonometry how you can rewrite this as a much cleaner expression. Okay? Collectively, though, do we understand that to find that segment area of the sector minus the area of the triangle? When I find the area of that triangle, I got to go back to, all the work we've done with isosceles triangles and understanding the relationships between angle bisectors. And then that brings in 30, 60, 90. My hopes, like I told you this probably a month and a half ago, special right triangles, SOHCAHTOA, are not going to go away, right? They've been around since the first day we learned about them. Okay, I'm going to open 10.7. It's called sectors. And that'll be due on Wednesday. You guys can go to lunch.